What specific problem does your method aim to solve in the context of evaluating LLM forecasters' predictions, and why is this problem significant?
Our method aims to address the challenge of evaluating the predictions of LLM forecasters, particularly in the context of long-term forecasting where ground truth resolutions are often unavailable. This problem is significant because traditional evaluation methods, such as backtesting, are limited by the lack of clear historical data for new types of questions, making it difficult to assess the accuracy of forecasts. Instead, we propose a consistency evaluation pipeline that utilizes logical consistency metrics to assess the coherence of LLM predictions, even when the actual outcomes are not yet known. By establishing principled metrics for consistency and demonstrating their correlation with forecasting performance, we provide a novel approach to gauge the reliability of LLM forecasters in a domain where conventional evaluation is infeasible. This method not only enhances the understanding of LLM capabilities, but also offers a framework for future improvements in forecasting accuracy.
Could you provide a detailed step-by-step illustration of how your proposed method for measuring consistency works, including the theoretical underpinnings and any novel components introduced?
Our proposed method for measuring consistency in binary forecasts involves a systematic approach grounded in two novel metrics, the arbitrage metric and the frequentist metric. First, we establish a theoretical framework that defines consistency checks as pairs of n-ary relations in question and forecast spaces, ensuring that all feasible forecasts satisfy these relations. The arbitrage metric quantifies the minimum guaranteed profit an arbitrager can achieve by betting against the forecaster's predictions, while the frequentist metric assesses how many standard deviations a forecast is from the mean of a Monte Carlo simulation, indicating its deviation from expected outcomes. Next, we implement a consistency evaluation pipeline that generates tuples of forecasting questions based on logical consistency rules, such as negation and conditional probabilities. These tuples are then used to elicit forecasts from various LLM models, which are subsequently scored for consistency using our defined metrics. Finally, we validate our approach by demonstrating that consistency scores correlate positively with forecasting performance, as measured by the Breyer score, across different forecasters, thus establishing a robust method for evaluating the logical consistency of LLM predictions.
Can you walk me through a specific example that demonstrates the inner workings of your algorithm, especially how you apply the consistency metrics to a pair of forecasting questions?
Certainly. Let's consider a specific example using the negation consistency check. Suppose we have two forecasting questions: will Trump be elected U.S. President, and will Trump not be elected U.S. President? The forecaster provides probabilities of 0.7 for the first question and 0.3 for the second. According to our negation check, these probabilities should sum to 1, indicating logical consistency. To evaluate this, we apply our arbitrage metric, which calculates the minimum profit an arbitrager could guarantee by betting against the forecaster's predictions. In this case, the inconsistency is evident because the probabilities do not satisfy the logical requirement, 0.7 plus 0.3 does not equal 1. Thus, the arbitrage metric would yield a positive score indicating a violation. We also use the frequentist metric, which assesses how many standard deviations the provided probabilities deviate from what a Monte Carlo simulation would predict. If the deviation is significant, it further confirms the inconsistency. This systematic approach allows us to quantify and analyze the logical coherence of the forecaster's outputs effectively.
What are the key theoretical and practical benefits of using your consistency evaluation pipeline compared to existing evaluation methods in forecasting?
The key theoretical benefit of our consistency evaluation pipeline lies in its principled metrics for measuring logical consistency violations, specifically through the introduction of the arbitrage and frequentist metrics. These metrics allow for a nuanced assessment of inconsistencies, accommodating the inherent noise in forecasters' outputs rather than treating them as binary consistent or inconsistent. Practically, our pipeline enables the evaluation of LLM forecasters using datasets with known ground truth resolutions, which is crucial for long-term forecasting where ground truth is often unavailable. Additionally, our findings demonstrate that consistency metrics correlate positively with forecasting performance, providing immediate feedback on forecaster accuracy without relying on backtesting, which can be challenging due to unknown training data. Overall, our approach offers a robust framework for evaluating forecasting models, enhancing their reliability and interpretability in decision-making contexts.
How did you validate the effectiveness of your proposed method, and what datasets or benchmarks were utilized in this testing process?
We validated the effectiveness of our proposed method by employing a consistency evaluation pipeline that utilized two distinct forecasting datasets, one scraped from prediction markets and another synthetically generated from news articles. These datasets included events that occurred after the training data cutoff for all forecasters tested, ensuring that they resolved before September 2024. We generated tuples of forecasting questions that adhered to logical consistency rules and associated consistency metrics, allowing us to assess the correlation between consistency scores and forecasting performance measured by the Breyer score. Additionally, we created a long-horizon consistency benchmark consisting of 3,000 consistency checks for forecasts resolving in 2028, which served as a testing ground for advanced LLM forecasters in scenarios lacking ground truth resolutions. The results indicated that our consistency metrics positively correlated with forecasting performance across the tested forecasters.
What specific results were achieved using your proposed methodology, particularly regarding the correlation between consistency metrics and forecasting performance in your experiments?
Our experiments demonstrated a strong positive correlation between the consistency metrics we developed and the forecasting performance of various LLM forecasters, as measured by the Breyer score. Specifically, we found that certain logical consistency checks, such as the consistency of conditional probabilities, COND, exhibited over 27% correlation with forecasting performance. This suggests that our consistency metrics can serve as effective proxies for evaluating forecasting accuracy, even in the absence of ground truth resolutions. Additionally, we observed that aggregating different consistency metrics improved the correlation with forecasting performance, indicating that a multifaceted approach to consistency evaluation is beneficial. Overall, our findings highlight the utility of consistency metrics in assessing and potentially enhancing the performance of LLM forecasters in long-term predictions.